In the chapter, you've learned the diversity of reactions you can use with the benzoic position. So we'll go through a few synthesis problems to put everything together. So the question here is, how are we going to get from this starting material over to the product? There are a few things we should notice right from the get-go. Is that in order to add this alcohol group, we need to probably add something to this carbon chain to start moving around. So we'll want to move around functional groups. That should lead you to think, okay, what are some of the few reactions I can use to add a functional group to a carbon without a substituent, or a carbon chain without a substituent? And one of the ways we can do that is using NBS and light, or heat. And that would get us, save time by drawing the aromatic differently, this bromine attached on that tertiary carbon. Now, as we compare what we just got to our final product, we realize that we're moving functional groups. So there's no way we're going to be able to add the alcohol group directly to here, but we need to move the functional position. So you should think, okay, one of the tools we can use to do that is to use an elimination to get the bromine to leave as a leaving group. So we can use a base that isn't sterically hindered, so sodium ethoxide would be perfect, because if we use a sterically hindered base, we're going to get the elimination across this bond right here. So we've done the elimination. Draw the aromatic again. We have our double bond right here. And now it's not too difficult. We just need to decide, okay, how are we going to add the OH group here at that sp2 hybridized carbon as opposed to this carbon? Well, this is the on the right, we have the anti-Marconi composition. So the way we can do this is using hydroboration oxidation. So we'll have our boron with this complex and our hydrogen peroxide with sodium hydroxide. And that will get us this product. And one thing you might notice as well is that, okay, hydroboration oxidation works through a syn addition, so we can actually go back to our product and add some stereochemistry if we want. Since it's syn addition, if we consider the OH to be on a wedge, then the hydrogen we added would need to be on a wedge, which we could then put the methyl group on a dash. And of course we would have our enantiomer, because we can attack from either side of the double bond. So in this reaction we saw a benzoic position. We noticed we could add something to that position to add a functional group. We moved the functional group by using an elimination, and we added what we needed after the elimination. Let's do another one, and in this problem I've incorporated things from earlier chapters just to reinforce some of the learning and understanding. Just to clear things up, we're starting here with this alkyne, and we want to consider, okay, what is this sodium amide going to do? Well, one way we might look at it is consider the acidity of ammonia, which is a pretty weak acid, so it would act as a pretty strong base. And we know that alkyne is actually a relatively good acid for being a carbon molecule. So the sodium amide is going to deprotonate the alkyne, forming an alkanite ion, and then when we add this group up here, our benzene ring with this primary alkyl group, then we're going to see an SN2 mechanism. So if we consider the, really quick, alkanite ion attacking this position, the bromine will leave as a leaving group, and thus our first intermediate with this question mark is going to look like this. Have the attack, bond, And there we go. Now we want to consider, what is this hydrogen with the palladium? Well, that should be relatively simple. We're just doing hydrogenation, so that's going to reduce these bonds to leaving us with a simple alkyl chain attached to the benzene ring. In this case, an alkyl chain of 1, 2, 3, 4, 5 carbons. Now that we're left with this benzene ring with a simple alkyl chain, then what are these reagents going to do? It should seem familiar that we're going to perform an oxidation, and with the benzylic position, it's actually in a way that we actually chop off, if you want to think about it, the alkyl chain, leaving just a carboxylic acid. So if I draw up here what we had after the hydrogenation, the 1, 2, 3, 4, 5, 1, 2, 3, and when we do the oxidation, we're essentially just going to cut this off and replace that whole group with the carboxylic acid, which means our final product after the oxidation is going to be this. Now keep in mind, when you're doing oxidation at benzylic positions, you want to make sure that you have at least one hydrogen on the benzylic position. Remember that with a benzene ring with a substituent like this, there are no hydrogens here to perform the oxidation, thus you wouldn't get an oxidation with that benzylic position. Now there are a few more reactions that are reviewed in the chapter over aromaticity, but you can learn those well enough by looking through the problem sets.